Well, good evening, it's Charlie here. The receiver is built. So what I want to do in this video here is just start off by just doing some pretty broad comparisons between the receiver and the commercial TS120 up there. And then we'll have a look at how it's been configured, and we'll go through looking at some of the design aspects that I settled on for the final receiver. So as you can see there, the receiver itself is drawing 115 milliamps with the screen on full. If I was to then drop the levels there, you can see the current dropping down, and with the screen off it's roughly 93 milliamps. So I was striving for around 100. Well, yeah, roughly 100. So I'm not going to grumble too much with being 10 milliamps over that. So in terms of actually doing this test here, I've got a very simple little crystal oscillator there that I use for just testing or trying to generate a very low level signal. It's got two crystals, one for the 80 meter band and one for the 40 meter band, so it's currently set to the 40, transmitting on 7030. That's the crystal we got there. So we'll just close that up, and that's then going through a little switched attenuator there, the output of which goes into that switch box there, which allows me to switch between the TS120 and the portable rig. So we'll start off with the TS120. So the plan is to drop down the level going in to the TS120, get it down to a level which the signal's way down in the weeds, and then we'll compare that with the portable rig. So we'll just crank the old volume up there a little bit. So that's sitting 700 Hertz low on the dial there to get the 700 Hertz tone. And we're currently there was inside the attenuator down here, we already have 20 dB, so just adding another 20 in there. We'll add another 20 in, and you may be able to hear that on the audio there. It's certainly getting pretty low. So we'll just flick across to this rig. And certainly you won't be able, unfortunately, be able to hear it on the camera there. I can't actually plumb the audio through, but that's certainly easily detectable. No problems at all. So we'll probably add in another. We'll add another 8 in. You can still hear that quite happy. 8 and 2 makes 10. That's certainly quite discernible, going up and down the frequency there. So go back to the TS120. And you can just hear it in the background. So, I don't unfortunately have good enough test equipment here to measure sensitivity levels. So all I can do is sort of broad comparisons like that, just to get an idea of the sensitivity of the receiver. But based on that comparison there, I'm more than happy with how sensitive that is, especially for such simple amplifiers. Nothing spectacular there at all. So that's good. More than happy with that. So happy with the current draw. More than happy with how that's performing at the moment. So let's disconnect everything, and then we'll go through and have a close look at the radio itself, and then look at some of the design notes, just talking about the various settings and some of the decisions that were made. So we'll just pause there, and we'll come back in. Right, so here goes the radio here. So it's all, as you can see, it's pretty well soldered down. So sort of just looking at the signal flow, and we'll try and talk about various aspects as we go through. The signal comes through here. On this side over here we'll have the transmitter, power input, antenna input, TR switch, but for now the receive RF is going to be coming through that little hole there, and into our bandpass filter. I'll talk about the bandpass filter design in a sec, but suffice to say, through the bandpass filter, which is tuned for 70-25, so halfway through the CW band, the lower CW band for 40 meters, the output of that goes to our RF amplifier under here. And I'll just pause there by saying, you can sort of see there that it's very much a game of Tetris with the PCBs. So what I elected to do is I worked out, or allocated space for each of the circuits. So the two IF amps, the AF amp here and the RF amp down the bottom there. And then once I determined that was the size of the PCB or the circuit board, I then sorted things down, knowing that at the end of the day it would fit all in, as opposed to just making it and then trying to make it fit. Anyway, so RF comes through the bandpass filter into our RF amplifier down there. That's the amplifier that we looked at a couple of videos back. The output of that RF amplifier then feeds into our mixer. Those are now SBL1s. Those sort of cheap ADE ones that I got in really did not work at all. I did some more experimenting last night with those, and they just did not perform at all per the spec sheet. So I'm not quite sure what was going on there, but I had some other SBL1s in the junk box, so we're using those. The output of the mixer then goes into the first IF amplifier down there, and like I say, we'll got another page we'll look at in terms of the transformer turns ratio there. The output of that amplifier then into the crystal filter. The output of the crystal filter then goes into our second IF amplifier here. That then feeds into our product detector, which is then receiving also our BFO frequency from the SI5351, which we'll look at in a sec. The output of that product detector is audio, which is through the brown audio, the grey audio cable there, and feeds into just hiding under there, running from there through to here, is the audio frequency amplifier there with their NE5534 just hiding under there, and then feeding up into our 3.5mm output for the microphones there. Those two orange wires you can see there coming from the 10K pot, that's feeding back into to be effectively RF in terms of our inverting op-amp amplification factor. So that works really well actually. So that's full volume, obviously, minimum volume just by varying that resistance, which is then varying that feedback value, which is then feeding into the equation. No change at all to the Arduino little Pro Mini and the display in the SI5351. That display, absolutely fantastic. I can't detect any noise at all. That seems to be working really, really well. So unlike with previous OLED displays, I don't have any problems at all with that. So at this stage of the game, I'm going to stick with that. And where I have in the past with IC2 noise with rotary encoder updating the screens, none of that. Absolutely deathly quiet, no noise at all, which is great. And our little Morse code keyer there, which we can talk about later on. I'm not quite sure exactly how I'm going to do that at this stage of the game. The original plan was to feed that third output from the SI5351 through that and then into our amplifier chain, but having just read that QRP Labs presentation that was presented a couple of days ago, I think I'm going to change my way of doing that now that I'm going to endeavour to try and work out how to make a Class E amplifier work. Anyway, so let's have a closer look at starting off with the bandpass filter. So the bandpass filter is the design that comes out of the solid state design for the radio amateur. There's quite a good appendix in that one which gives you various values that you can then using the equation you can work out the various values. So I did a mixture between the values that were for a 7 to 7.1 meg filter and the one for the 7 to 7.2. I did that because I found a happy medium between the two where I could use some standard values. So the way it worked out in the end, you define for a start your end capacitors, and like I say, using a bit of a combination between those two values, I settled on 39 picofarads. 245 from this equation here, C0 minus C12, which is our capacitor between the two tuned circuits, which was 5 picofarads, which is again a happy medium that was provided, minus our CNs. You can then work out from that equation there what the value is, or the total value of capacitance across the inductor. So it turned out to be 201 picofarads. So what I opted to do is I've opted to use a 180 picofarad fixed capacitor in parallel with a small trim. So if you look back here, you can see that there. So we've got our incoming 39 picofarad capacitor there, we've got our fixed 180 picofarads in parallel with our little trimmer there, in parallel with our inductor, which we'll talk about in a sec. So that was the values for the capacitors, so our incoming capacitors, our parallel capacitors, and our trimmer. Now for the inductor, the original inductor called out in this particular circuit utilized the T68-6, so it wanted 20 turns using number 22, which would have given us an inductance of 1.88 microhenries. That's the T68-6 there. That's quite large. Absolutely no problems using that in say a base rig, but given the sort of tight real estate there, I didn't particularly want to have a large inductor, so what I elected to use was to rejig it around the smaller T50-6. So knowing that 20 turns on the larger toroid gave me 1.88, I could then reverse engineer what would be the closest whole number turns to give me around that number. So for the T50-6, again using number 22, in fact I actually used number 26 in the end, I got 22 turns. So those inductors there in the filter themselves are 22 turns on a T50-6. And it tuned out really nicely. So like I say, tuned for roughly 7025, and first time in a long time actually, the overall parallel capacitance with that inductance was such that when I did tune that variable capacitor, the little trim pot, through 360 degrees, so one full revolution, I got the two peaks, which was good. So I knew that I was actually getting to maximum resonance on that particular that tuned circuit there. So that was good. So that's the bandpass filter, and then into the various amplifiers. So the amplifiers themselves are exactly the same as we looked at for the RF amplifier. I just elected to use the same core in terms of the actual transistor itself, the 2N3904, its biasing and its decoupling capacitors, exactly the same. So that core is the same as this core over here, is the same as our first RF amplifier coming in after the bandpass filter. So that's exactly the same. The only thing that changes is the coupling transformers between the various circuits. So just taking a snippet from the block diagram, the output of the SBL1 is 50 ohms. that needs to feed into the IF amplifier, which has an input resistance of 186 ohms. The output of the amplifier, so that's the first one. The second one will need to match the output of 200 ohms through to our crystal filter of 500. That was a guess, and I did some sweeping this morning with a SIGGEN and just sort of swept across it with various terminating impedances, and in terms of the passband ripple, 500 I should say, seemed to be about right, and it certainly sounds good, so I've elected just to stick with that. So like I say, that second transformer, 200 to 500, the output is then 500 to 186, so the input to that's the IF amplifier. The second one, the output is 200 then through to our product detector of 50. So here goes the 1, 2, 3, 4 transformers that we need to wind. They're all FT37-43s, and they're all using number 26 for the wire. So looking at that first one up here, so the turns, to work out the turns ratio and then the number of turns, so 50 times n squared needs to equal 186. So we can rearrange, so 186 divided by 50 square rooted gives us an n of approximately 2. We'll just round that sort of up to 200 just to keep the maths nice and easy for this particular one. It gives us an n equals 2, so we'll pick on 8 turns to 4 turns. Now, rule of thumb is for the smaller winding, so this 4-turn winding, it needs to be a minimum of 4 times its impedance that it's seeing. So the 4-turn side is going to be on the 50 ohm side, so we need to see at least 200. So a 4 turns on an FT37-43 gives us 5.6 microhenries. We know that our inductive reactance equals 2 pi FL, where F is 9 megahertz, which is close enough to that 8999.3. So let's just round that to 9 megahertz to keep it nice and round. Gives us an inductive reactance of 316 ohms, which indeed is greater than 4 times 50. So that's good. So that's an acceptable turns ratio for our primary and our secondary. Well, it doesn't really matter, but suffice to say the smaller winding of those two. So the second one here, 200 to 500, exactly the same process. So 200 n squared equals 500, gives us an n of 1.5811. So we'll use 11 turns to 7 turns. So 11 divided by 7 is close enough to 1.58. Again, taking the smaller winding, that's going to be seeing the 200 ohms. So let's work that one out. So 7 turns on an FT37-43 gives us 17.15. XL equals 2 pi FL, plugging it in gives us 970 ohms. So 970 is indeed greater than 4 times 200. So tick. So that's good. So that's again an acceptable turns ratio there. I won't belabor the point here, but exactly the same process for the next two transformers. So 186 n squared equals 500. Work it all out. 10 to 6. Looking at 6 turns gives us 712, and that indeed is pretty close. We wanted 744, we're getting 712, so close enough to 4 times that, so that's good. And then same with our last one, 500 n squared equals 200, so that's 200 to 500, so again 200 down to 50. Gives us an n equals 2, work it out, 8 turns to 4 turns, and then we can pull that value down from the top. And indeed 316 is greater than 4 times 50. So those 1, 2, 3, 4 transformers are what we see there. So there goes the first two, 1, 2, and then 3, 4. And the one we saw the other day for the RF amplifier just sort of sneaking down there, we've already looked at. So I think that's all I really wanted to cover off on this particular one. Let me just check my notes there. So we've looked at the signal strengths. I'm quite happy with that. We looked at that, we looked at the... yes. So what I do need to do, I didn't have the real estate on this side to have a little RF attenuator for the incoming signal. So for a really strong signal we don't want to overdrive the circuit. So what I'll do here on the antenna when it comes in, we'll have a small 10k pot, which just allows me to act as a very crude but quite effective RF gain control for the overall radio there. Let me just come out a bit. So next steps now are to look at the amplifier. So that needs to fit in the side down here. Like I say, want to make that a Class E amplifier. So that was a really good steer that was suggested on a previous video, and having now looked into it and reading that article from QRP Labs, I think that's really the way to go for this CW transmitter or transceiver. So that's what we'll be looking at. Haven't got my BS170s yet, they're on order, so we'll just sort of keep doing some design work and then we'll work out how to make those work. And that article did also make a very good point, which I had thought about but neglected, but I've sort of gone back to thinking, well, actually I should really do it, is just looking after key shaping, just to make sure we've got a, if we can try and get a cosine waveform on our transmitted CW would be nice. So we'll have a look at that as well. I think that's all for now. I won't talk about any of the transmitter circuits anymore, but suffice to say it's all in, which is great. I had to sort of build it in stages, so put one in and then do the connecting wires, put the next piece on. In the past I have built quite a tight one before, and I tacked down all the circuit boards and then attempted to do the power wiring and the signal wiring, and it just gets too fiddly, you just can't get the soldering iron in. So it was a much better idea of sort of starting at one end and but like not such a jigsaw puzzle, but sort of just building across. That seemed to work quite well. Anyway, so I'm more than happy with that. That's certainly not going to go anywhere. And like I say, the normal process for these, if I can find the cover, is so that's how it's transported around the place, and then for operation the cover comes off, and then we're into it. So I'll say 73 is there. Any questions, sing out. Otherwise we'll continue to do some looking into how we're going to make this, how this transmitter works. Anyway, 73 is all. Thanks very much, and we'll go from there.